Hi everyone, welcome to session 18 on advanced algorithms. We started talking about approximation algorithms last time, and we saw an example of a very simple algorithm. Here it is for the vertex cover problem. So it's a hard problem. Vertex cover is NP-complete, as you know, but you can easily derive a two approximation for the problem if you choose an inclusion maximal matching and just pick both vertices of all the edges in the matching. And we've discussed last time that there are tight examples that show that it's quite unlikely that you can improve upon this approximation. So unless you're happy with the two approximation, you have to work much harder for the vertex cover problem. Today we look at another topic that you're now already very familiar with, namely randomization, and that it actually goes nicely hand in hand with approximation. And the reason is that we've seen for randomized algorithms we can often profit from repetition. And for optimization problems, it's a very natural idea to just repeat some random process several times and then pick the best solution that we found. And often we can prove an approximation guarantee for such a method. Now there's different possibilities how you could define this. I would say that this is maybe the most natural way. If you like, it's let's first see the definition. So we have an optimization problem as we defined it at the very beginning of the course, and we fix a parameter delta. That's our guarantee. And an algorithm is called a randomized delta approximation for the problem that we are looking at. Well, if it's always computing a feasible solution, otherwise it's not an algorithm compatible with the problem. And with probability 1/2, the solution that we return is at most within delta of the optimum, where we defined this approximation ratio like 1 plus the relative difference, so the cost that actually our algorithm returns, and the optimal value for the given instance x, and we divide that again by the optimum to normalize. So we've seen the example for vertex cover where delta was 2, which just meant that the cover that we return was never more than twice as bad as the optimal, and we can have the same kind of definition is used here. If you like, we're using a one-sided error Monte Carlo method for delta approximation. So in a sense, this is and because we won't have any other kinds of error Monte Carlo methods here, we'll just put randomized to indicate that it's only with a probability 1/2 that we get this approximation guarantee. There's a different notion that is maybe not as natural if you come from the randomization chapter, but actually it's often easier to prove that you have an algorithm of this kind. The setup is the same, but now we only consider the expected value of the approximation ratio, and we are happy if the expected value is less than delta. I should add, so the expectation is just with respect to the random choices of the algorithm. Just to make that clear again. so the random bits that we use in our computation, and it must be true, this inequality must hold for every input x. This is implicit in these definitions. We've always used it like that. I just wanted to emphasize it one more time. Now let's see some example for randomized approximation algorithms. And for that, we go back to one of our toy problems that we've studied in the FPT chapter, namely the max-sat problem. We're given a formula in K, C, and F. And we're looking for an assignment that satisfies the maximal possible number of clauses. We're not necessarily interested in satisfying all. We're just asking for a maximal number. We make a normalization assumption here, if you like, that each clause contains exactly k literals and from k different variables, so no clause should contain duplicates or a variable and its negation. These cases are easy to remove in a pre-processing, so this is not really a restriction. And you can also just fill up clauses with boring variables in case you have the desire to do so. Actually, I think if the clauses are smaller, the results will, this algorithm will work the same and the results will only get better. So no, not necessarily. So we need that assumption here, and it might in some sense be a bit of a pain to transform a formula to one that's max-sat equivalent and has exactly k literals per clause if we don't allow duplicates. Let me just say that for this application here, it's really a toy problem. I don't know of any real applications for max-sat anyway, so let's just take this assumption here because it makes the analysis much smoother. So the algorithm that we use is as trivial as it can get. You just guess an assignment and return how many clauses are satisfied by this assignment, and that's it. And we're claiming that this already suffices to be an approximation, and actually not even a bad one. This algorithm is a 2 to the k over 2 to the k minus 1 expected approximation for the k max-sat problem. So k is just the parameter they have to fix. And if you insert k equals 3, then this is 8 over 7. And the same algorithm is also a randomized approximation where we didn't take the expectation, but it has this guarantee half of the time. And then you get 4 over 3 for k equals 3. And actually these get better if you increase k. So this is not so bad, which actually shows our max-sat problem is a relatively easy one from the point of view of approximation. So let's see how we can prove this. The vital observation is that a single given clause, I'll just write it as a set of literals, as we've done several times before. Such a clause is satisfied by an assignment whenever at least one of the literals is true, which means it's not satisfied when all are false, And if we take a random assignment, as in the algorithm, uniformly at random sampled from all the 2 to the n in this case, if we have n variables, sampled uniformly from all the 2 to the n possible assignments, then a single clause is not satisfied by a random assignment. With probability 1/2 to the k, because we have literals that stem from different variables. This is where this assumption comes into play. And so all of the k literals have to fail their Bernoulli trial. And then this is the probability that it's not satisfied. So of course this means satisfied with probability 1 minus 2 to the minus k. Now, this is true for every individual clause. So let's define if our formula phi consists of the clauses C1 up to Cm, then we use these indicator random variables Zi that are true if the ith clause is fulfilled. And of course, what we've just shown or argued is that these have these probabilities, but the individual Z's are not independent. Otherwise, the task of satisfiability would be pretty easy. I mean, there can be special cases for formulas where they are independent if every variable just occurs in one clause. But these are not the kind of interesting formulas. In general, they are not independent. But what you always can do is just sum up and use linearity of expectation. If we define Z to be the sum of these indicators, and this is actually the cost, which is a positive thing, a good thing, the value of the solution that we return in this case. And then just by linearity of expectation, we get this expected value of satisfied clauses. So that's the expected number that we get by just randomly guessing an assignment. And of course, the optimal solution can't do more than satisfy every clause. So this can be at most m. And that immediately gives us that well, let's just write it like this. The approximation ratio of our algorithm, I called it random assignment. So you might add here random assignment for a given formula is, well, that's one more step. It's a maximization problem, so that means you divide opt by the solution that you get, and that's just Z. And by this bound, this is at most m. The expectation here we can compute. And well, you can rewrite this as in the claimed form, which is a bit nicer than having the negative powers. Otherwise it's the same, so of course you cancel the m here. And that already proves the first claim. So that was kind of easy. For the second part, this is what I mentioned before, right? The expected approximation claims are often easier, whereas for these ones we have to work a bit harder. But maybe I should have added here something where we defined it. If we are given a delta expected approximation algorithm A, then we know that the approximation ratio of this algorithm is at most delta. And since the approximation ratio is a positive quantity, we can use Markov's inequality. To find that the probability that this is less than 2 delta greater is at most 1/2, and therefore our algorithm A is also a 2 delta randomized 2 delta approximation, sorry. So this shows that there is some relation between these two, and as soon as you've shown something about the expectation, you also know something about the probability, but making the guarantee twice as big is relatively pessimistic. And we will see that in most examples, in most concrete applications, we can actually do something better than just applying Markov's inequality. So if we come back to our random assignment for the max-SAT problem, then here, of course, you could just double this factor and use the procedure that I've just outlined. And then you immediately have that the same algorithm is also a, well, 2 times this randomized approximation algorithm. But if you look at this, this is not quite twice the number. You can actually show something better. So for part 2 of the claim, we have to work a bit harder and look a bit closer at the problem at hand. And if you look at the number of satisfied clauses, then there's the expectation, which was m times the probability to satisfy an individual clause. And since there was an upper bound here, if you just intuitively assume that Z has about the same kind of dispersion to the right and to the left, you might expect that it's possible that half of the assignments are actually to the right of this point, which is m times 1 minus 2 to the minus k plus 1. So you make this probability essentially a bit smaller. You allow a bit of slack here, and then you have the same kind of distance from the expected value in both directions. So there's a reasonable chance that if the expectation is so high and you can't go higher than m, that you also usually don't go much lower than that. Having said that, this is an intuition, but it's not a proof, because for wicked distributions of this variable set, this would be entirely wrong. such an argument does not work in general. But in this case, our Z does have a nice enough distribution so that it's possible. And the point that we can make is we define the number of assignments that fall into this range, denote that by L. The number of assignments alpha with less than m times this smaller thing satisfied clauses. Well, and symmetrically the other ones are called U. Then we know that the two together must be all possible assignments for n variables. And we can also give a bound using our expectation. Where we just, for all the small variables, we use the largest value that's the possible contribution from all the assignments that correspond to this small class, which is this. And for the other ones, for U, the largest contribution they can give to the expectation is M. And well, if you just expand these, you see that this implies that U must be larger than L in this case. And all that we needed to apply this is actually this upper bound on this cost value here. And therefore we immediately have that the probability that the random assignment approximation ratio is less than this smaller thing here. So I should divide the optimum by our cost. So here the +1. So this is greater than 1/2 because we just have more assignments to the right of this point than to the left. And then again, this inside of here, if you cancel the m and rewrite the fraction, you obtain the claim. Okay. I'd like to show you another example It's also a simple algorithm, but maybe less of a boring example, because at least the underlying problem is NP-hard. So we're looking at the max cut problem. Given a graph, you're looking for a cut, so a bisection of the set of vertices, so that you have the maximal number of edges in the cut. So that this is NP-hard might be surprising, because the similar problem of a min cut is actually in P, and we've seen a good randomized algorithm for that last time. But the max cut problem is NP-hard. But still, it's relatively easy to approximate, at least to within a factor of 2, by the simple procedure called random cut, where you just, for each vertex, assign it to a random side of the cut and just return whatever you get. That's about as easy as it can be. And also the proof that this is a 2 expected approximation is very easy. We have a variable for each edge, and this is 1 if this edge is a cut edge. And this is exactly the case if U is in one set and V is in the other set. Oh, this doesn't work like that. I should have called them 0, 1, then you could do this trick. Let's just write it like this, or vice versa. Well, you know what? These names are just arbitrary. So this is exactly cut if one of the vertices is in V1 and the other is in V2. That's just by definition. And since we assign these randomly to these two sets, whenever you're given 2 nodes, there's 4 different ways to assign these two nodes to the 2 sets. And out of the 4 assignments, 2 give this situation, and the other 2 don't give it. So the probability for XE is just 1/2. Or I should write the expectation or the probability that it is 1. Now again, the XEs for the different edges are not independent. In fact, they are pairwise independent. But as soon as you have such a triangle, these are not independent. If you know whether these 2 edges are in the cut, then you can deduce whether this one is in the cut or not, and there's no randomness, so they can't be independent. But that was the same situation for the last algorithm and for the expectation. If we just sum up all the edges, then surely we get just half of all edges in expectation. And since the best that the optimal algorithm can achieve is to cut all edges, we immediately have that the expected approximation ratio of the random cut algorithm, which is dividing optimum by x, and this is just at most 2. Well, that already proves this theorem, and you might have noticed that in this case there's the second part missing, that this algorithm is also a randomized 2 approximation without the expected. And the reason why this is missing is that I'm convinced that it's not true. The problem is that these edges are quite strongly interdependent, not independent, and therefore it's not so easy to extend this. We can do it still if we amplify the probability to get a good cut. So here's our second try. We repeat for a magic number of times to compute random cuts and just return the largest one. And then this actually gives you a 2 approximation in the randomized sense. And the proof is a bit different from what we've seen before, maybe. Let's say, so x is again, as before, the number of cut edges. And we're interested in this probability that we have at least half the edges cut, because that will give us the 2 approximation by the same reasoning that we've seen. Well, and now we apply essentially the same trick that we used before. When we were talking about the max-sat problem. But this time the probability that will come out will be a bit different, and therefore the result differs. X equals I. I'm just rewriting the expectation by splitting the sum in 2 halves. And that's essentially in slow-mo what we've done before for the other problem. And so this I here can be bounded by m½ minus 1. And the sum of all the probabilities, once this I is out of the sum of all these probabilities is just 1 minus p, because that was the probability to be in the right sum. And the right sum, the upper bound for I is m, and we have p for the sum of all these probabilities. And if you again simplify that by just expanding, you find this. So p is greater than 1 over m½ plus 1. And that's not quite a half, right? That's usually a relatively small number. But still, if we keep on repeating, then the expected number of trials we need until we find one large cut that has at least half the edges cut. The expected number of such trials is 1 over p, so m½ plus 1. And then by our famous Markov inequality trick, the probability to need more than twice the expected number, so more than m plus 2 trials, is at most 1/2. And if you check back, that's exactly what our algorithm is doing. And therefore, this algorithm is actually a randomized 2 approximation. But it's a bit unfortunate that we need so many repetitions. And in fact, you can do much better by a very simple algorithm that doesn't even use randomness. But it's, in a sense, inspired by the algorithm we've seen before. And so it may help you to prove this theorem that this greedy max-cut algorithm is a 2 approximation, because that's what I intended to give you for the exercises. So we've now seen 2 examples of problems that are easy to approximate to within a reasonable factor. We've seen 2 approximations for both of them. We'll now turn to a problem that will turn out to be a bit harder to approximate and a bit harder to deal with in general. And that's the problem, that's the set cover problem. And I call it the Drosophila of approximation, because we will see that many different techniques that are helpful for approximation algorithms in general can be exemplified on the set cover problem. And so here it is. I call it weighted set cover because we have these costs. So what's the task? You have a universe given by just the number n, so it's the numbers 1 up to n implicitly. And you've given k subsets of this universe. And you're looking for a selection of the subsets that, if you take the union of all of them, give you the whole universe. So you cover every element in the universe by at least one of the subsets. And the cost function just tells you how much you have to pay for selecting each of these subsets if you include them in the solution. Now, this problem actually generalizes the vertex cover problem, which immediately proves that it's an NP-complete problem. Whereas for the vertex cover problem, the universe corresponds to the set of edges, and you have a set for each vertex in the graph, and this just contains all the edges that are incident to the given vertex. And then you see that cover has to give you all the edges in some way by selecting a subset of the vertices. So that's exactly what we require for the subset, for the set cover problem. You additionally have the feature that, well, for one thing, the vertex cover problem is usually not formulated as a weighted problem, so the cost to include one node is just 1, which is a special case of this. You can, of course, also think about a weighted vertex cover problem where the nodes have weights. But there's another special property of the vertex cover formulated as a set cover instance, and that's that each element of the universe appears in, well, exactly 2 of the subsets. That's just the case because every edge is incident to its 2 endpoints, and that's it. Whereas in the general set cover problem, there's no restriction. An element could appear any number of times in any number of subsets. It would be helpful if it appeared in at least one of those, otherwise there's no feasible solution. So that's one assumption we will usually make. But apart from that, it can appear in many subsets. A simple method to tackle this problem, that's probably the easiest, or the first one that you would come up with, is just to greedily select the set that currently gives you the most new element for the least cost. And that's exactly what this algorithm does. If you look behind the formulas, what's happening here, that's the crucial step where you select the next subset to be added to your solution. You take, so this is the cost of the subset divided by the number of new elements that it buys you. So this is, in a sense, the per element cost that you have to pay if you include this. And you choose a set that minimizes this per element cost. So you could say you try to add just a single new element that you have to cover, and you do so for the least cost that you can do. Well, of course, in general, if you add a new set, then you will in one shot get several new elements covered. But that's fine, right? We have to cover all these elements in the end anyway. So I added here a few parts for the analysis. That's nothing that the algorithm will actually execute, but it's helpful to refer to these quantities in the algorithm, in the analysis, as if the algorithm would compute them. So we just count from one starting the sets as they are added to the cover. And we remember this per element cost that we paid, and that's the alpha I. So alpha 1 is the per element cost for the first set that we take into our solution, and so on. And whenever we add a few elements, for those that we added, we remember their price, which is exactly this per element cost. And as we will see, this is actually something we can nicely control. So here's the corresponding lemma that gives you a bound on these prices. And for that, we assume that we now relabel our elements of the universe in the order in which the algorithm includes them or covers them. Now, several of these elements are included at the same time, so you just arbitrarily choose one of these orders. And then you can show that the price of the element that's added as the ith element is at most this, the cost of an optimal solution for the instance, divided by this quantity n minus I plus 1. Now, let's see why this is the case. So consider EI that's added in some iteration of the algorithm. And at that point, we had a certain number of elements that were already covered. And we're particularly interested in the elements that are not yet covered. So this set C bar is the set of all not yet covered elements at the beginning of the iteration, where we in the end add the ith element. And well, a trivial observation is no matter how we started our cover, we can always complete the cover, the set cover, with at most cost opt, because we can just at any point decide to now include all of an optimal solution. I mean, from point of view of the analysis, of course, we wouldn't like to really have to compute the optimal solution. But at any point in time, it can't cost more than to add all of the optimal solution to get some cover that extends what we currently have. And since EI is the ith element added, we know that well, already I minus 1 elements are in the cover, which means that the uncovered elements by just n minus I plus 1. And if we take this cost that we need to, that we at most pay to finish the cover, and divide it by all the elements that we still have to include, then this is an per cost and per element cost, which is precisely the term that we're looking at here. Now, the argument is we can finish the cover with this per element cost for the whole rest of the cover. No matter how we start it, opt additional cost is sufficient to complete the cover, and with the completion we add exactly n minus I plus 1 elements, and that in turn means there must be some I star that has at most this optimum, this per element cover given by this opt over n minus I plus 1. Otherwise it's not possible to have this value over as an average over all of the rest of the elements. If all, so it's a simple proof by contradiction. If all of these alpha I star were strictly greater than these, then it wouldn't be possible to complete with costs opt the cover that we currently started. And well, this is the set that we now add, and that means that's the price that we charge to element EI. And that's already it. An almost immediate corollary is that the greedy algorithm is an HN approximation for the weighted set cover, where this again is the harmonic number. And as you know, this is essentially ln n. So we now have an approximation guarantee that's not a fixed constant, but it's actually depending on a parameter, namely n, the size of the universe that we're considering in the set cover instance. Now, why is that? Of course, we use our lemma. The overall costs of the cover that we compute by greedy set cover is just the sum of all the element prices, because whenever we add a new set, we have to pay this cost C of Si, and we divide it by the number of elements that we add. So if we sum over all elements, then this fraction is just canceling with the number of elements that we add. Well, and then well, up to that point it's an equal, and now we use our lemma from above, the price lemma, which just says we have opt as a factor, and then these fractions n minus I plus 1, and if you now sum in reverse, what's the smallest term that we get? If we insert n, we start at 1. If we insert 1, we go up to n. That's just hn, the nth harmonic number. So we've shown that the cost of our algorithm is bounded by hn times opt. So it's an hn approximation. Now again, you can ask yourself the question, this log n, roughly log n approximation doesn't sound too great. Maybe we can do better. The reason, well, can we do better? No. At least not easily. The first answer is not with this algorithm. So it's not a matter of improving the analysis of the given algorithm. You have to work on the algorithm itself. And for the proof, we just take as an example, as a tight example of, well, it must be an infinite family. So let me just draw that like this. We have the elements 1 up to n, and then we include one large set that actually contains all of these elements, and we assign it cost 1 plus epsilon. And then there's additionally singleton sets that just include one of the elements each, and we make the first cost 1 over n, the second 1 over n minus 1, the next one 1 over n minus 2, up to 1, which would be the last term. Now if you closely pay attention what the greedy algorithm does, and initially it compares the cost efficiency of these, and you find that 1 over n is just a tiny bit better than 1 plus epsilon over n. So you will decide to take this set, and then with the next set you have the same kind of comparison. This is always a tiny bit better than the 1 plus epsilon, so you will have to take all the singleton sets, which gives you exactly hn as cost. Whereas of course the optimal solution would have been to take the large set. And well, you can make the epsilon arbitrarily small, you can make the n as large as you like, or large or small as you like. So this proves there can't be an analysis showing that this greedy algorithm has a strictly better approximation ratio than this harmonic number. Okay, so maybe we should try a different algorithm. And there's a nice technique that's a bit specific for set cover, but still it's quite elegant. And let's try that and see if we can do better. We need a few definitions for that technique. The first thing is a cost function is called size proportional if it is essentially assigning a set its cardinality as cost, well, with potentially some factor, but since it's the same factor for all sets, it doesn't really matter too much. And then we also have another term, the frequency of an element of the universe is just the number of sets, the number of subsets Sj where this element occurs. And we talk about the maximal frequency of an instance, or just the frequency of an instance. And by that we mean just the largest, so the frequency of the most frequent element. Now, for vertex cover, I already mentioned that we will always have a fixed frequency of 2. And it's actually for all elements the same, right? So this may motivate for you why this definition might be interesting, because we've seen that if we take a special case of the problem, then this f becomes easier. In the general case, you can't really say anything about f. It can be up to k. All sets can contain an element. Now here's a really trivial observation. If we do have such a size proportional cost function, we can very easily get an f-approximation. And the idea is the approximation is simply taking everything. So if you take the cost of all the sets, that's by definition just summing up the costs of the individuals. Well, and since we assume that this is a size proportional cost function, what we get is essentially this. And now we rewrite this sum. Here we just sum up the sizes of the subsets, but we can also write the same thing as sum over all elements in the universe and just sum up their frequencies. Because here you sum up all the sizes of the sets, you will have added every element as often, you will count every element as often as the number of sets in which it appears, and that's exactly this. Well, and this is bounded by f, so it's p times f. But well, that's, oh, sorry, there's a factor missing. Of course, we just sum that up, so here's another factor n missing for the size of the universe. That's where things get where there's another factor missing. And the optimal value of a solution, it has to cover all n elements. So it has to select somehow some subsets so that at least all elements are covered. Well, and then we have this factor p because the cost function is size proportional. And well, that's a lower bound. It will not usually be possible to attain this, right? But certainly we can't do better than that. If you combine these two, then this is f times opt, as we claim. So if we happen to have a size proportional cost function, an f-approximation is trivial to get, and this is actually how we can do vertex cover. And the result just tells us to take all the vertices, right? If we have unweighted vertex cover, where each vertex just adds you as a unit cost to the overall cost, then this is certainly a size proportional. Oh, sorry, no, it's not. I'm sorry. The cost of a vertex in vertex cover is always 1, but that's not size proportional because the subset lists here are the incidence lists. Okay, so this is a trivial observation and it's not per se useful. But we can make this an algorithm that actually is useful, because if you like, you can see any cost function that you get as a size proportional cost function plus some residue. And you can reverse the process. You can just subtract from a cost function the size proportional part and try to deal with the residue in isolation. And that's what the following algorithm here is doing. And that's why the technique is called layering. You try to find layers that are size proportional in an arbitrary given cost function. So first of all, you try to find the largest cost proportional part, which means you take the cost of each set and divide it by its size and take the minimum of all these ratios. Therefore, thereby you make sure that the residue is never negative. And then this is the size proportional part. As I write size proportional part, as I wrote up here. And here is the residue, and this is always greater or equal 0 by construction. And then you look at all the sets for which the residue is 0. These are the sets that actually form a size proportional subproblem. And then you try to take all of these elements all of the subsets that do have a 0 residue, because we know that for the size proportional part by our observation, it suffices to just take all the sets to get an f-approximation. So you can just go ahead and try whether, if you take all of these sets in the C0, if that already gives you a set cover. In that case, you just return that and be happy, because that's by the observation already an f-approximation. In the other case, there's a few sets that do have such a residue and are needed to get the cover. And then you recursively solve the part with only the residue cost function. And you only consider the part of the universe that's not yet covered. That's also clear. And you can restrict attention to all the sets where you don't yet know whether you have to take them, and that's exactly those that intersect with the universe U1. So the algorithm is still relatively simple and straightforward, but maybe it's not immediate that this is actually giving you a sensible solution to the problem. But what you find is that this layering algorithm in total actually gives you an f-approximation. So like in the simple case where you have this fully size proportional function, with this recursive approach you can get the same guarantee for any cost function. Now before we prove that, let me comment on the quality of that. Whether f-approximation or hn approximation is actually better is not, it's the two results are incomparable in quality. For the vertex cover problem, we definitely we definitely know that the f is always 2, so this is the much better solution for that problem. But for other cases, it might be different. and well, f can be as large as k, whatever that is. So let's prove why this is an f approximation. The first thing is that we should show that it actually returns a set cover. Even that might not be trivial in that case, where we explicitly check that all elements are covered. This is certainly correct. But the interesting part is this, where we recursively continue. But there we can, by induction, use this result. So by induction on the number of recursive calls, you find that every call returns some cover for the set, for the universe that it's given. And here you just take the union of the two. So that part is actually relatively easy. The more interesting part is the approximation guarantee. Now, we again do this by induction, and again on the recursive structure. So the base case is that we don't have a recursive call, but we'll just end up in this case. And that's a plain application of the lemma that we've just had. So that's actually easy. So the hypothesis is that the recursive call returns an f approximation. So let me just write that C1 is f-approx with respect to the sub-problem, which was we consider the universe U1 and the subsets that are only interesting. And the important part is it's an approximation with respect to the cost function, the residue cost function C1. Now to do the inductive step, we need a bit of notation, I guess. First of all, let's denote by C star an optimal vertex cover, a set cover. So optimal for the complete problem with respect to the original cost function. Then we can define C star 0 as the set of all indices of subsets, so that the subset is completely contained in the universe for which, so the elements that have 0 residue. That's what C0 was. That's exactly how we defined that here in the algorithm. That's all the subsets for which the residue cost is 0. And now C0 star is from an optimal solution, all the subsets that fall into this categories, residue 0, and then C1 star is just the rest. Now we have by inductive hypothesis the condition for the C1 part. And we also have for the C0 part, so this is the size proportional part of the overall cost. So that means this set that we compute in the case where we have a recursive call, this is an f-approximation with respect to the C0 cost, simply because this is size proportional, so we are allowed to just take all the subsets. So if we decide to take a smaller subset, that's definitely only better. So that's an f-approximation, but only with respect to this C0 cost function. So that's nothing more than saying that the cost in this cost function is at most f times the one for our C star, which is just one specific cover. So we can actually squeeze in between here f times opt with respect to C0. But all we need is this bound. Then we use the inductive hypothesis. So if we take the cost function C1, clear, so C1, the small c is the cost function. By inductive hypothesis, this is an f-approximation for the problem with the residue cost function, and then by the same argument you can also insert here any specific cover. And if we combine these two things, then we find that the cost of our entire cover, which can be written as the sum of the two parts of the cost function, we've just defined them so that they sum up. Then for this part, we can actually restrict attention to the sets that have non-zero residue. So these are only terms of size 0 that we drop here. Well, then we use what we've just derived about our sets here. So that's these two equations that we use. F times C0 of C star plus C1 of C1 star and then we can also add here again the sets that actually have residue 0, and then we find that we have at most f times the cost of an optimal cover. So that concludes the inductive step, and it concludes the proof that our layering algorithm for the set cover problem is an f-approximation. Okay, we'll see next time a less trivial application where we will formulate an interesting problem as a set cover instance, where you have to work a bit harder than for the vertex cover problem.